This is the first of what will be a series of 3 short videos that will be used to try to explain why it is that calculus is used pretty much all the time when you're trying to evaluate the results of experiments, and also when trying to study equations such as those associated with the various laws of nature. These equations, therefore, would be able to explain many different everyday observations. I'll start this little introduction to calculus by looking at 2 very simple cases. The first one involves a car that's driving along a flat highway at a constant speed of 30 miles an hour. 30 miles an hour is the same as 44 feet per second. And this highway will have a line going across it, which we'll call the starting line. So we'll call time equals 0 the time when this car that's going at a constant speed crosses that starting line. And the position of the car we'll call x equals 0 at the time that the starting line is crossed. So the first figure is going to show these variables at the top of the figure, and also a couple plots at the bottom. The variables dx and dt are also introduced here, and they're used all the time in calculus. Dx just means the distance that the car has gone during a time interval dt. And what's really important is the ratio of these 2 numbers. So dx divided by dt is called the derivative of x with respect to t, and that in this particular case is the distance the car goes per second, and so that's the speed of the car. So this is all that a derivative is. It's just the ratio of dx divided by dt, and that's going to give you some new information here. So we plotted, in this case, x versus t in the right-hand plot at the bottom of the slide, t in the horizontal axis and x on the vertical axis. So dx dt is the slope of that line, and it's 44 feet per second. And that is the speed of the car. So the slope of the line of x versus t, in other words, x is 44 feet after 1 second, 88 feet after 2 seconds, and so forth. The slope of that line gives you the velocity of the car, and that's the derivative of x with respect to t. And we can also plot the velocity versus time, which is done on the left-hand plot. That's not as interesting because it's a horizontal line, which has 0 slope. And so it says that the velocity is constant, which is what we started with, and the slope of the line with the constant velocity has 0 slope. dv dt, therefore, is 0, and that means the velocity is not changing. If dv dt in general would be the acceleration of the car, if the velocity was changing every second, then the car would be going faster or slower, and then this line would have a slope to it. But in this case, the velocity is not changing, so the slope is 0. We can look at a little more interesting case by putting in an acceleration, and that's shown in the next of these figures. So at this time, I picked the car starting off at 0 velocity, stationary, but with an acceleration of 22 feet per second squared. So that means that the car's speed goes up by 22 feet per second for every second that passes, and that's plotted in the middle panel. The left-hand panel is a slope of that line, which is the acceleration. In this case, it does have an acceleration. It's 22 feet per second squared, but the acceleration is constant here, and so that line has a slope with 0, graph has 0 slope, whereas in the previous case, the velocity line had 0 slope because the velocity was constant. This figure here also shows a third panel on the right-hand side, which is the position of the car as a function of time. And qualitatively, you can see that looks reasonable because this car started at 0 velocity, and so the plot of x versus t, the position versus time, has essentially 0 slope at the beginning, and the slope keeps increasing and increasing as the velocity increases. And so you could expect a curved line like that for the position of the car. In other words, it doesn't go very far in the first second, but in that third second, it goes a lot farther because the speed is increased by that time. Well, you don't really make plots like this when you're doing calculus. You don't measure slopes and make plots of x versus t or v versus t. You use some equations, and that's what's going to be shown in the next slide. So it's a much quicker way to get derivatives. The top line in this will show the particular derivative that will be important here. But first, let's look at the third line up from the bottom, because that's the equation that I'll be deriving the third of these three videos, and that gives you the position of a constantly accelerated object, like the car. So that third line from the bottom says that x, the location of the car, is equal to x naught, the location where it started, plus v naught, the initial speed, times the time, plus 1/2 the acceleration, a naught, times the time squared. Well, we know all those numbers in this case. In fact, for the second figure that I showed, the x naught was 0. It started at 0 position. And the v naught also was 0. It started at rest. So the only non-zero term is that third one. And you can put in then the 22 feet per second squared and get what the position of the car was at any time. And that's given at the end of this third line from the bottom. It's 11 t squared feet. So that's the location of the car at any time as a function of time. And that's that curve plot that I had in the previous figure. Now, if we want to get dx dt, though, instead of making plots and measuring slopes, you use what's in the top line of this panel. There are three terms in this equation that we just looked at. The first one was at x naught times t to the 0 power. T to the 0 power is just 1. Plus the v naught times t to the first power, plus 1/2 a naught times t to the second power. So there are three different powers of t that come into those three different terms. And the expression at the top line, gives you the derivative of anything that is that format. In other words, if x is proportional to t to some power, you can use that top line to calculate what dx dt is very quickly. And so, for example, the only non-zero line is going to be the one with t squared in it for this particular case. And so x will be proportional to t squared. And then n in that x equals t to the nth power, n will be 2. And dx dt will be 2 times t to the n minus 1, which is first power, so it'll be 2t. So I just put down in that, took those two equations on the top line and put in n equals 0, 1, and 2, which are going to be corresponding to the three terms that will be important in this case. And then wrote down what x is for the three cases and what dx dt is for those three cases, all using just that information on the top line. So in other words, we have now x is equal to 11 t squared feet. And so if we want to get the velocity, we take dx dt, the derivative of x with respect to t, using that information in just the top line, we can write down that very quickly. And that is what's shown in this line just above the second line from the bottom. And that's 22 t feet per second. That's the speed of the car. So after 1 second, it would be going 22 feet per second. After 2 seconds, it would be going 44 feet per second, and so forth. So that gives you the correct velocity of the car, just using that one expression, a very short expression at the top, without making any plots or without measuring any slopes. And then, since we have v now, then you can calculate the acceleration, which is dv dt. And again, using that same expression at the top, but now we have the velocity was 22 times t, and so using the line with the n equals 1 line, which is a function of t to the first power, we see that the acceleration on the bottom line is 22 feet per second squared, which is, of course, what we started with. So anyway, what we've done here is to assume that we knew the position of the car as a function of time, which is the third line from the bottom. From that, we calculated, using that one expression at the very top of the slide, we can calculate the velocity, and from that line, then we have the velocity, we can calculate the acceleration. So we're going down in that list of variables. We knew x, we can calculate v, we can calculate the acceleration. Now you can go the other way. And that's what we'll do in the third slide. That's called integration. And so you can start with the acceleration and calculate the velocity and calculate the x. That's what we'll do in the third of these little videos. But anyway, this is sort of the kinds of things you do in calculus, and the results are very quick to get very often, and much quicker than trying to make plots and measuring slopes and areas and things like that.